Before starting, it is important to state that all the material presented in this video has been peer-reviewed by experts in the field. It has been published in the RevStat Statistical Journal by the National Institute of Statistics of Portugal. P-values exhibit some counterintuitive behaviors. For instance, even if the pairs P1, 0.05, P2, 0.10 and P3, 0.90, P4, 0.95 are formed by p-values that differ by the same amount of 0.05, the information contained in the regions identified by these two pairs differs substantially. To understand why, it is sufficient to consider that the ratio between the first two is exactly 2, while the ratio between the second two is slightly larger than 1. In other words, thinking of p-values as probabilities, in the first case, P2 is twice P1, while in the second case, they are almost equal. However, having to consider the ratio between two p-values every single time is quite impractical and inconvenient. Furthermore, as extensively discussed in the recommended literature, distinguishing between arbitrarily close values is often inconclusive or even scientifically incorrect. For this reason, the use of Shannon information, also known as Surprisal or S-value, has been proposed based on the following reasoning. Given the probability P of an event, this can be related to the probability of obtaining S consecutive heads by flipping an unbiased coin using the following formula. Thus, we obtain the following logarithmic relationship between P and S. The aim is to compare statistical significance with a phenomenon that we are familiar with in everyday life. However, mathematically speaking, it is fair and important to acknowledge that the S-value measures continuous information. It is up to the reader to interpret that information in relation to the context. For example, values such as S equals 4.3 cannot be understood as 4.3 consecutive heads. However, this can be interpreted as when all the background assumptions are true, the statistical result is approximately as surprising as 4 consecutive heads or slightly more than 4 consecutive heads when tossing a fair coin. So it is now very easy to observe that the informational difference between the previous pairs is marked. Indeed, we have 1 bit in the first case and 0.08 bits in the second. The problem is that surprises can be effective in properly evaluating statistical surprise, but they cannot address the common confusion about the difference between that surprise and magnitude. As a matter of fact, a statistical phenomenon can be rare or unexpected, but weak, meaning it may have a little practical impact. For example, while following a weight loss diet in accordance with the health recommendation of their primary care physician, one may consistently lose about 1 gram per day for 100 days, which is a scientific effect that is unlikely to be due to chance, but still be far from their target weight. Indeed, losing 100 grams in 100 days has a negligible impact on physical health. In order to properly evaluate the statistical magnitude, or rather, the effect size, some authors have proposed using multiple confidence intervals, or better, compatibility intervals, and observing how the statistical surprise changes in relation to the variation in effect size. However, this poses a clear asymmetry in the definition and application of the concepts of compatibility interval and statistical surprise, since the former remains confined by definition within the scope of statistical significance or compatibility. Moreover, one may easily think that a situation like this is symmetrical with respect to the central interval when, in fact, this includes very different confidence requests or compatibility requests. Indeed, as we saw before, the amount of information contained in pairs of equally distant p-values can change dramatically. These are the reasons why we are going to discuss two main points. The first is the concept of surprisal interval, which can address the issues related to the obscured relationship between compatibility interval and surprise. And the second is a novel convention to compress information on the relationship between S-value and surprisal interval. Let's consider the case of a normal distribution and assume we want to find a Fourier interval, for example. The corresponding exact p-value is, according to the shown formula, 0.063. Therefore, the corresponding compatibility interval is, according to the following formula, 93.7. Now we need to ask ourselves, what is the value of z for which the area under the Gaussian curve between minus z and z is equal to 0.937? Here we can see the answer to this question. So basically we are dealing with another kind of compatibility interval, but in this case, in our new fashion, the interpretation is extremely different. Indeed, if and only if all the background assumptions are true, all target assumption prediction that lie inside the Fourier interval are less surprising than getting 4 consecutive heads when flipping a fair coin, compared to the calculated experimental result according to the chosen statistical test. So let's suppose we choose a specific statistical test and consider a target assumption predicting an effect H. Let's also suppose we calculate an experimental result R, for example, the difference between two population mean values, when all the background assumptions are considered true. So the 4E contains all and only the values H, such that the difference between R and H is less surprising according to the chosen test than 4 consecutive heads when tossing a fair coin. According to this, a formal definition of surprisal interval is as follows. If and only if all the background assumptions are true, a surprisal interval, or S-interval, is the interval that contains all and only the target assumption predictions that are less surprising than S consecutive heads when tossing a fair coin, compared to the calculated experimental result according to the statistical test. In this regard, I invite you to consult the proposed example in which I calculate different surprisal intervals, in this case 6, 5, and 4 intervals, and I present them through a novel compact form, a novel convention, through which you can observe easily how statistical surprise changes in relation to the variation of the effect size.